So our speakers, Linus and Nicholas, have devoted their professional careers to ESO. They've been visitors to Congress since 30C3, and now, from our previous talk about a space-based telescope, we're going to learn all about the extremely large telescope, which is based here on planet Earth.
Hello everyone and good evening. We are going to talk about the Extremely Large Telescope. First, about us. We both work at the European Southern Observatory, or short ESO. Nicholas works as a software engineer on the observatory control software.
And Linus works on adaptive optics control software. Now, let me start with a few words about the European Organization for Astronomical Research in the Southern Hemisphere, or a bit shorter, European Southern Observatory, or usually by its acronym ESO. It is an intergovernmental organization that has been formed in 1962 and at the moment has 16 member states, which are the ones with the flags that you see here, and one special member state, which is Chile, which is our host country. And in addition, we also have Australia as a strategic partner. These member states define ESO's mission, which is to design, build, and operate advanced ground-based observatories and to foster international collaboration for astronomy. ESO is, I think, or at least from my personal experience, not so widely known. So often we are confused with ESA. ESA is a completely different organization, founded a couple of years later. ESA does space telescopes, rockets, satellites, these kind of things. ESO does ground-based astronomy. So our headquarters are located in Garching by München. This is at the same campus where for example, the TU Munich has a number of departments, and also various Max Planck institutes are there. All our telescopes are actually located in the Atacama Desert in northern Chile. We have about 750 staff. 2/3 of them are working from Garching, and 1/3 of them is working in Chile. The member states' contribution in 2021 was 192 million euros. So these are your tax euros that is spent on ESO. And here you see the locations of our observatories. So Santiago is the capital of Chile. And the oldest observatory is La Silla that we have, which is close to La Serena. And then the Paranal Observatory on the mountain Cerro Paranal, which is close to Antofagasta. Then Chajnantor, close to San Pedro de Atacama, which is then close to Bolivia and the Argentinian border, and the ELT, which will be located, or is being constructed at Cerro Amazonas. So why are all those telescopes in the Atacama Desert? Well, if you look at this picture, which was taken on a service mission of the Hubble Space Telescope, you see that there are no clouds. It is a desert that is very arid, so no humidity goes in this area, and in addition there are very high mountains, and this makes very good conditions for astronomy, for ground-based astronomy in particular. So La Silla, as said, was our first observatory that started in the 1970s. There are a few telescopes from us, but nowadays also a lot of telescopes from the national institutes, for example from the Max Planck Gesellschaft, and they reuse the infrastructure that we have at the site and just operate their own telescopes there as well. Now, on the mountain Cerro Paranal, we have, for example, the Very Large Telescope, VLT, which consists of 4 unit telescopes with 8.2 meter diameter, so these are the big ones. And then, in addition, 4 small telescopes with 1.8 meter diameter, which are called auxiliary telescopes. And in the optical spectrum, the Paranal Observatory is considered our flagship facility at the moment. Then, a couple of years later, there was also the Atacama Large Millimeter and Submillimeter Array went into operation. It is located at an altitude of 5,000 meters, which is very high, on a plateau called Chajnantor. And this is a joint project by ESO and North American and East Asian partners. And these are 66 radio antennas that can also be moved around and also operate as an interferometer.
Okay, so why do we want to build another telescope? Scientists, or specifically astronomers, want to study Earth-like exoplanets. They want to look for biomarkers on exoplanets. There's the dark matter, which they want to study and understand better. And there are faint objects in our solar system which are difficult to observe, but also interesting for astronomers. Therefore, we need a telescope which has a high angular resolution, which means that we need a larger primary mirror diameter. And we want to increase the light collecting surface, so we need to increase the mirror size. And with more light, more fainter objects are observable, and we can use shorter exposure times to see them. So this is a rendering of the ELT, what it is going to look like, roughly. It will have a 39.3 meter primary mirror. If you look at this room, from the width of this room is 36 meters. So the primary mirror would not even fit in here. This is the sheer size of the mirror. The site is Cerro Amazonas, which is at 3,045 meters, which is roughly 23 kilometers east of Cerro Panal, where the very large telescope is. It will cost around 1.3 billion euros, and that is for the construction period from 2014 to 2028. And the first light will be approximately on 2028, at the end of 2028. There are two similar projects. There's the Giant Magellan Telescope, which is 25 meters, and the 30-meter telescope, which is 30 meters in size. Now, if you can see here is a size comparison of the ELT. On the left, this is the Berliner Brandenburger Tor. I don't know how many of you have been to Berlin. This is 20 meters high. The dome, or the building of the ELT, will be 80 meters high. The dome, so the top part, will have a diameter of 88 meters. And the building on the ground, this is the auxiliary building, will have a diameter of 120 meters. The dome, so the top part, is there to protect the telescope from the environment. So this is the sun, the wind, the temperature, so temperature differences, dust from the desert, and rain. There is a ventilation and air conditioning system to prevent dome seeing. Dome seeing is when you have a different air temperature inside the dome than outside, so you have an air movement from inside the dome to outside, and that creates distortions of the light, which you want to avoid. So the dome is cooled to the outside temperature, and this ventilation and air conditioning system needs 3 megawatts for operation. This allows the dome to be cooled down by 10 degrees over a period of 12 hours. There's also a windscreen, which you can see between the two doors. This is to deflect away the wind that is directed at the telescope. The reason for that is that if there is wind pushing against the mirrors, it would make pointing of the telescope difficult. So in order to prevent the wind of pushing too much against the mirrors, there is this windscreen. Also, because we are in a geologically active region, we have seismic isolators for the telescope itself, and the telescope and the dome, so the main structure is the telescope, and the dome are on different foundations, actually. So this is the main structure. So the inside, what is inside the dome, you can see this is the platform on which it rotates, so horizontally, where it will rotate like this. Then you have the primary mirror here. There's a mirror tower where the other mirrors are. There are two instrument platforms here and here. So the instrument is basically what collects the light and analyzes it, or is a camera, or can be a spectrograph, for example, so to see what spectra of light is emitted by some part in the sky. And there is also the altitude axis, which goes through here, so the pointing and the height.
So the ELT has a unique optical design, which consists of 5 mirrors. You can see here, so the mirrors are just called by the order in which the light hits the mirror. So M1 is the primary mirror, then there's a secondary mirror, M2, and so on. M4 is also interesting because it has a hole, so basically the light goes from M2 through M4 onto the M3. So here this animation shows this a bit nicer. So the light hits first M1, M2 goes through M4, hits M3, now it goes to M4, is reflected a bit off axis onto M5, and now to the instrument platform. And then overall, of course, there are more mirrors than just those 5, but those are the main mirrors in the telescope itself. So the primary mirror, there's usually the problem when building mirrors. If you use a monolithic piece of glass, you can go up to approximately 10 meters diameter. So for example, for the VLT, it's 8.2 meters. So nowadays, well, okay, one could probably go a bit more. But the problem is that as you increase the diameter of the mirror, if you tilt the mirror, for example, to the horizon, it will deform under its own weight. So you have to increase the stiffness of the mirror. You can achieve this by making it thicker. So you add more glass, you add more mass, and then it gets still reasonably stiff, so that it does not deform that much under its own weight. But you hit a certain limit at roughly 10 meters. So for example, for the VLT, we have about 30 centimeters of glass, and for 8.2 meters, so it's basically just the glass itself is about 23 tons. This, of course, makes the mirrors very expensive. Also very difficult to produce because you need a very high quality glass that has no errors basically in the glass, no air pockets, whatever in it. And it's also very difficult to transport, for example, by truck or by ship. If you think of it, for a 39-meter mirror, you cannot transport it on any road. Think of the size of this room. So what is done for those larger mirrors is to segment them. So here you can see a rendering. You see all those small little segments. And these together, so these have to work together. These are individual segments, but they have to work together to form the optical shape as if it was a monolithic mirror. If we look at this, for example, for the M1 of the ELT, it means we have 798 of those hexagonal segments. Each segment is about 1.9 meter across. In addition, we have 133 spares. They have a coating made out of silver, which has to be renewed every 2 years. And in order to not have to stop operations for many years, recoat all the mirror segments, basically we have to exchange 2 segments per day and put them to the recoating and take out 2 segments from a spare set of segments and move them back in. There's a 6-fold symmetry, so which is what you can see here. So you see here all these are individual segments. And there's a 6-fold symmetry within one of those sectors with 133 segments. Every segment has a unique shape. So we cannot simply swap out segments as we want. So that's why we need a complete spare sector of 133 segments. And they all, as said, they have to work together to keep their position and their shape as if it was a monolithic mirror, and it has to be at an accuracy of a couple of tens of nanometers. So here's a rendering of one of those segment units. So this is one segment. The part that will be coated consists of a 50 millimeter thick piece of Zerudur, which is a special glass ceramic, which has a very low thermal expansion. You can compare this to Ceran, which is basically the more consumer-grade product, and Zero Dur is the industrial-grade product of this glass ceramic. As said, it has about 1.4 meter across. The segment itself comes with a so-called segment support, so some mechanical structures underneath it, which the entire unit then has a weight of about 250 kilograms, and this is what is lifted out and replaced. The segments have a couple of degrees of freedom. So, for example, here on the bottom, you see those three cylindrical things, which are called position actuators. These are allowed to change the piston tip and tilt of the segment. Changing the piston means if we have two segments, you can move a segment up or down, and the piston has to be done in a way that the phase, so the position of the segment basically has no jump going from one segment to the other segment. Tip tilt means we can rotate basically the segment around two axes. How do we know the shape of the overall mirror? So this is done by so-called edge sensors, which are located here at the edge of the segment. These are coming in pairs, so there's basically one transmitter element here and a receiver element on the neighboring segment, and here vice versa. And these allow us to measure piston, gap, and shear to the adjacent segment. So overall, this is about 4,500 of those edge sensor pairs. And in addition, there are 9 shape actuators, which are called warping harness. These allow us to push or pull on certain areas of the mirror to move it a bit up or down by a couple of nanometers or micrometers and change the optical characteristics of the segment. This is necessary, for example, for seasonal changes. If we have a 39-meter mirror, we have about 2 centimeters of thermal expansion just of the steel structure underneath, and then it would not fit anymore their actual placement as it was foreseen of the mirror. So this is why the shape has to be adjustable on a slow scale over seasonal temperature changes. For the edge sensors and position actuators, the control loop runs at 500 Hertz, so every 2 milliseconds we gather all the sensor data from all the segments. It goes into a big matrix vector multiplication, and the control matrix and the output are the new positions for the position actuators every 2 milliseconds. So this is, for example, these are a couple of segments at the factory of the polisher, and you can see some humans here in the back. So the segments themselves are not really that big. You can see here that this is just the glass as it is without any coating, and you can also see some of the bond pads where basically the support structure is glued onto. Now the M2 and M3 are relatively simple mirrors. But the M2 is complex to produce. So it is a convex mirror with about 4 meter diameter and highly aspheric. And it's the largest secondary mirror that has ever been produced. And because it's highly aspheric, that also makes it very difficult then to produce. M4 is a bit simpler, just 4 meters, and not so complicated. Both of those mirror units can be controlled with a hexapod system that has to have a sub-micron precision. So it's about 3 tons of glass and 12 tons for the total assembly.
Okay, so when you look from the ground into the sky, you go through the atmosphere. And when there are different layers with different temperature in the air, you get the distortion. You see this when you look over a street, and on a hot day, you see this, that the light is basically distorted. Objects will appear blurry, and if you look in the sky at the night, when you see stars twinkle, this is the same effect. To counter this, there is a technique called adaptive optics, so it makes the optics adapt to the distortion. How this works, there's a short video. So you have some galaxy that you want to look at. You see the light is coming here from this object. And when it goes through the atmosphere, it is distorted. And when it comes to your telescope, you will get a blurry image. So what you do is you take an image with a special camera of a so-called reference star, and you use this camera data to calculate the shape of a deformable mirror. And this is done by the adaptive optics system, which does this 1,000 times a second. So this deformable mirror changes the shape so that the wavefront that is before distorted is now corrected and is no longer distorted. And in the end, you will have an image that is as sharp as if you wouldn't have the atmosphere at all. So you need a reference star. You need a bright one. Not always you will have a bright one that is near the image, near where you want to take the image. So what we do is we take lasers, which have 20 watts of optical power, and we shoot them in the sky. They excite sodium atoms in the upper atmosphere, which is at 80 to 105 kilometers. And also the system has an automatic shutoff when an airplane approaches to prevent accidentally blinding the pilot. So here's an image which compares the non-adaptive optics versus adaptive optics. This is of Neptune. It's taken with the same telescope, just switching off the AO, the adaptive optics system. And as you can see, the resolution is increased dramatically. So the deformable mirror of the ELT is the M4. It is a 2.4 meter diameter mirror. It is only 1.95 millimeters thick. It is put on a reference body, which is made out of silicon carbide for the stiffness and low weight. And there are 5,352 voice coil actuators, which is a similar principle than a loudspeaker. So these are magnets that push or pull on parts of the mirror. The mirror is actually made out of 6 parts. You can see this on the reference body. This is not visible here, but it's basically the mirror has the same parts. And the displacement can be by up to 50 micrometers in each direction. And the mirror can be updated up to 1 kilohertz. This is a bigger image of the M4 together with the reference body. And then we have the M5. This is a flat mirror. It's elliptical. It does tip-tilt correction, so again, movement like this to stabilize the image. This is also part of the AO, where you just do this part on a different mirror. This mirror must be lightweight and very rigid because you want to do these corrections very fast. And you don't want the mirror to deform, and you want it to be light so that inertia isn't a problem. And there's also a switching mechanism for the M5, which is different from the tip-tilt, which allows you to switch between the 2 instrument platforms, which are on opposite sides.
So now this video takes you on a flight into the ELT. So first you see the mountain, Serra Amazonas, with the ELT on top. The dome, as said, has a height of 80 meters. And if we now enter the dome, we can see the main structure inside. Now we move up to the platform that rotates, so that horizontally rotates, the azimuth platform. And you can see also here in yellow, these parts are the laser launch telescopes for the laser guide stars, basically. So this platform here is about 10 meters above the ground. And now we go to 27 meters above the ground to the instrument platform, which is then where all the spectrographs and imaging cameras and so on will be located. Here on the right, you see the closed doors of the dome and the windscreen. The doors now open, and the windscreen moves up together with the altitude movement of the telescope, and now also the lasers turn on. So far you have only seen the renderings, but how does it look like at the moment? As we said, it is under construction, so it's not yet complete, but this is a photograph taken, I think, about 4 months ago. So you see that actually you can already see the dome. You can also see all the auxiliary buildings. These are cranes, actually quite big cranes. We can also look inside. So here there are also some cranes, but also here there are humans, the construction workers that are currently working there. So this is about the size of this telescope. Also here is a crane inside the dome, and there's another one here in the middle. And with this, we want to thank you for your attention. Here are our contact details, and we can now also answer your questions.
So for those of you in the room, we have 4 microphones set up, not 5,000 voice coils, just 4. And for those of you on the internet, we are monitoring Matrix, we are monitoring IRC, we are monitoring your thoughts if you post them in Mastodon. We are in the Granville room, so please use the appropriate hashtags and IRC channels, and we will try and bring your questions. We have more than 10 minutes for questions, so I think we'll be able to get through quite a few. And I see that there are quite a few lining up everywhere. Let's start in the back.
Hi, thank you for your talk. I have a question about disturbance in the in space, because there is a lot of space trash, the satellites, something like Starlink or so, and I heard that these are disturbing the images taken from astronomers. So is this a problem for you as well? And is the project still usable in like 5 years?
So there was a study that was made by ESO, and we looked at especially Starlink, and it had an impact, but you can eliminate the trails of the satellites from your images. If you take multiple images, you can reject the pixels from that one image, and it wasn't so bad as we initially thought. Yeah, that's all I can say to that.
And especially the ELT is a telescope that has a very narrow field of view. It is not a survey telescope. So if you only look at a very tiny piece of the sky, the probability that exactly at that moment you have as one of those satellites crossing the image is very low. So the ELT itself is not affected, or not really affected. But survey telescopes, for example, that regularly scan the entire sky, they are affected, and also radio telescopes. So this is why usually you have an exclusion zone around those sites that they do not get jammed basically by the satellite communication.
Okay, thank you.
So I've received an optical signal from the internet that the internet has a question.
Hi, we have a question via IRC, and which is, since there are so many movable parts on the different mirrors, how long are they estimated to remain operational?
So the minimum lifetime for the ELT is 30 years. We hope it will be much longer, but it's at least 30 years.
Thank you.
So here in the front, microphone number 1.
Hello, thank you again for the very great talk. I have a question. Will one be able to visit this in person? Because I want to see a mirror this big.
I don't know for the ELT, but for the VLT there is the possibility. I think every Friday there are school classes going there, so you can visit the operator room and the telescopes. Maybe this will be done for the ELT at some point as well. I don't know. We have to see.
Thank you.
So the other side in the front.
Hi, do you also clean the secondary mirrors, and if you do, how do you? Because I guess they're quite big.
Yes, so they are 4 meters, but they have to be cleaned regularly as well. There is normally, so for example, that can be done with like a CO2, for example. so just some dry ice. And if they need to be recoated, then it has to be done, yes. Then the telescope will be out of service for a while. But the thing is, if you have basically dirt on the mirrors, means they just get a bit more and more blind over time. But since we collect so much light from the primary mirror, at least the other mirrors, it's not that bad if they are a bit degrading over time.
Thank you.
In the back.
Hi, so thanks for the talk. So you mentioned this climate control system for 3 megawatts, and it has to work 12 hours to reduce 10 degrees.
Yes.
So basically my question is, like, when the night comes, the temperature is constantly changing, and how it managed to equalize? So like you need to predict, use like a weather prediction to predict the temperature or some...
Yeah, exactly. What the idea is that you put the telescope dome to the temperature that it will have when you open the dome. During the night, you will have, there are ventilation, basically parts on the side of the telescope, which allow air to flow through. So then it's no longer really a problem. But during the time when you open, you don't want to have a temperature differential between the outside and the inside of the dome.
So it's basically you open the door when the temperature stops changing outside, roughly.
So basically we are following the ambient temperature. So during the day we have to prevent the dome of heating up. But, and that's why we cool it down to the projected temperature at night. And then during the night, there's still some air conditioning going on, but we can also open these are called louvers, so these openings on the side that basically go around everywhere. And these allow us just to take in the air from the outside as it is. And ideally, we have a very laminar flow of air over the primary mirror. And we can also control which side, so depending on the wind direction, for example, we don't want the direction where the wind comes from, but maybe a bit to the side. So this way we can control basically how much air goes in and out. And that then means that the inside of the dome has the same temperature as ambient temperature. So we can avoid this dome seeing. And there are also no other heat sources like computers and so on allowed directly in the inside the dome basically, and they have to all be outside in those auxiliary buildings.
Got it. Thanks.
My eyes have detected some stray photons beaming to us from the internet. Could it be that there is another question?
You're right on that. And the internet asks if the reflective surface is just the silver coating on top, why the mirrors need to be made of glass and not something lighter?
So traditionally, this 0-2 is chosen because it has a very low thermal expansion. You can use, for example, beryllium, which is the material used for the James Webb Space Telescope, but beryllium is even more expensive than 0-2.
Up front, microphone number 1.
Hi, so there's the very large telescope, the extremely large telescope, and there were plans about an overwhelmingly large telescope. So I guess you know what I'm asking. What's right with naming? Except for fun, of course.
The naming is, because we are an international organization or intergovernmental organization, we cannot, if you look at other telescopes, they're usually named after people, and we cannot really take one person from one member state, maybe. That would be unfair. So usually, all our telescopes, there's the 3.6 meter telescope, there's the new technology telescope, all of them, they are very generic and not for a person, more like what they are, no fancy name. Except, extremely large is quite fancy, I guess.
Seems legit. Thanks.
In the back.
Maybe more of a personal and philosophical question. Why
Careful.
do we need to explore the space? What does it bring us?
That is something that you would need to ask an astronomer, which I'm not. But in principle, there are science, you want to know basic fundamentals of how things work. And actually in space, there are a lot of things where we don't know how things work, and they are quite fundamental. So I mean, if we, for example, look at dark matter, we don't know how that really works, is my understanding. So this impacts our basic physical laws. And unless we figure that out, there's basically, it's unclear if they're really correct.
Okay, thank you.
All right, we go to the other microphone in the back, but please no existential questions.
So, given that the telescope consumes several megawatts of electrical power, I imagine you would need fairly visible transmission lines, which I didn't see on any renderings or aerial photos yet. And neither did I see any solar farms in the nearby. So, how do you basically?
So for the ELT, we have our own transmission lines that go through the desert. Okay, they are not our own ones, but they, on that occasion for the ELT, they also built transmission lines through the desert, which did not exist before. We are connected to the Chilean grid. There's, in addition, in between Cerro Amazonas and Cerro Paranal, in this plain, in this big valley, basically, there is also a 9 megawatt photovoltaic plant, which during the day basically would take some of this load, but of course not during the night.
Okay, thanks.
But basically, yeah, it's a fair question. For example, the VLT, the Very Large Telescope, ran for many decades basically on diesel generators and gas generators. And also for a couple of years now, it's also connected to the Chilean grid. While we still have those gas turbines, which can also be used for balancing the grid, which is also a very nice point because it's really in the middle of the desert.
Microphone 1.
During the starting question, you mentioned exposure times. What kind of dimension of exposure times do you usually get? Like, is it seconds, minutes, hours? And how does it compare with this telescope to the other ones?
I'm not a scientist, so I don't. I mean, I've been to Paranal, but I don't know how much they usually take for these exposures. To be honest.
So it's minutes to hours.
Okay. Yeah.
Thank you.
Could it be that the internet has another question that does not take minutes to hours to answer?
We can try. Why do we still need space telescopes when the atmospheric distortion is correctable?
That's a very valid question, and we have a bonus slide for that. If you look at this image, you will find that there are some parts of the electric spectrum which is basically completely absorbed by the atmosphere. So in the gamma and X-ray spectrum, you have this, and then in the longer range of the infrared, and in the long wavelength radio waves. And there you basically need to go to space. There's basically no other way, because you won't receive anything on Earth. So if you look at the long infrared, this is basically the field of the James Webb Telescope, for example.
So I think we have time for one more question. We're going to take it from the back. Oh, sorry. I've just been informed by the audience that we're taking it from the front in the right, so please.
How is the observation time divided? Can I buy a time slot, or are there specific proposals from different groups to use that time?
So basically, there is a process where the principal investigators plan the observations. They have to say which instruments do they use, and so on and so forth, why they exactly need those instruments, those facilities, that they, for example, have also exhausted alternatives for doing this. So, for example, it would be a waste of time to start or do an observation on the ELT, which will be overbooked probably for a very long time, oversubscribed for a very long time. And then, okay, you notice that, okay, you could have done the same thing with another investigation first on another telescope. And if you have clear evidence on those other telescopes, then probably you will also get to the ELT. There is no... let's say there are no nationwide quotas, basically. So there's a competitive process. The proposals will be reviewed, and the best ones will be taken, and most feasible ones will be taken.
Thank you.
And let's collectively thank Linus and Nicholas again for their fantastic talk.